We're going to talk a little bit more about, you guessed it, angle, side, angle. This time relating to parallelograms. Once again, guys, I feel like students in general are pretty good about understanding the general definition or the general postulate that is angle, side, angle. The trouble comes in identifying it in context, especially when it's embedded in a proof or just surrounded by a lot of other information. So a quick refresher, our angle side angle theorem tells us that if we have two triangles and we know that two sets of corresponding, remember corresponding means that they're in the same relative position in two different polygons. If I know that two sets of corresponding angles and their included side are congruent to one another, then the triangles are congruent. Let's take that through one more time. If I can establish that these two angles are congruent to one another, that these two angles are congruent to one another, and that their included side, the side formed between them, are also congruent. Another way to think about that is the vertices of each angle. So the vertice for this angle is right here and right here. The line segment formed between them is the one that counts. For example, if I knew that these two angles were congruent, and I also knew that this was the congruent side in my two triangles, that ultimately wouldn't be very helpful because that's not the included side. Okay, and again, talking specifically about angle, side, angle. Notice that the order of the acronym, angle, side, angle, kind of clues you in, right? You have an angle, an adjacent side, and another angle adjacent to that side. Okay, now I don't want to overdo it on explaining angle, side, angle. If you want to know more about it, go check out my asynchronous session on angle, side, angle, and other postulates. Again, I've noticed a little bit of difficulty in just identifying it in context, and that's nothing to worry about. It's just something we need to practice. So I wanted to review an example of this. Say that you know that this figure ABCD is a parallelogram. That means that two pairs of what sides are congruent? Well, the answer to that is opposite, and I'm just kind of going over that because that's not my focus here. Hopefully you know that, and that's from just the definition of a parallelogram. Again, since ABCD is a parallelogram, the two pairs of opposite sides, meaning AB and CD, so AB and CD are congruent, and then BC and AD are congruent. Okay? And then the next thing they say is that since angles 9 and 11 are vertical angles, that they are congruent to one another. So sure enough, if you look at angle 9 and angle 11, they are congruent. Okay. Next they say that since this is a parallelogram, AB is parallel to CD. AB is parallel to CD. Since 2 and 5 are alternate interior angles, 2 and 5 are alternate interior angles along these parallel lines, we can allow that those two angles are congruent. Okay, so I know we're kind of gathering a lot of congruencies here. In fact, let me change colors. We're gathering a lot of info here. I swear it's building to something. So we've established a couple of different congruent lines. I'm going to pay attention. Notice I'm marking this congruency with one tick mark, but it's in red. That's my way of indicating that it's different from the single tick mark in green. Okay, so those two are congruent. All right, so we're establishing all these congruencies. So we've gone through these couple steps. Next we say since two angles of triangle AEB are congruent to two angles of triangle CED, the third angle theorem supports that angle 8 and angle 3 are congruent. So let's look at those two triangles. So that was triangle AEB, this triangle, and triangle CED. So third angle theorem tells us that if two of the three are congruent, then you can assume that the third one is as well. Okay, Now remember, this doesn't mean that the triangles themselves are congruent. There's no angle, angle, angle postulate. But then they say, therefore, using the blank, it can be stated that triangle AEB and CED are congruent. Well, like I just said, there's no such thing as an angle, angle, angle theorem. What are we using here? We are using angle, side, angle. We're using angle, side, angle. And let me illustrate it. Let's illustrate it. The side that we're talking about is this one on the perimeter of that parallelogram. So we know that that side and this side are congruent. Now remember, with angle, side, angle, you have to be talking about two angles in their included side. So automatically you know I must be talking about this angle and this angle, right? We had established that each of those sets of corresponding angles were congruent, and you can see I've got an angle, a side, the included side, formed between this vertice and this vertice, okay? And then the proof goes on. So my point really wasn't to go over this proof, rather to show you how it can get a little cluttered identifying these postulates. It would have probably been pretty tempting, since you had just established that all three sets of corresponding angles in those two triangles were congruent. I think it would have been tempting to say, oh, it's because of angle, 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 okay? So you really need to be up on your postulates and theorems on that. Use that reference sheet I've given you. Keep it handy, and again, draw pictures, mark them up, do whatever you need to do to keep your information straight, because I know you guys can get this, and I don't want you to lose points, just due to being unorganized or being rushed. So really take care to highlight or label things as you go, and again, pay particular attention when identifying whether angle, side, angle, side, or other postulates and theorems as you go. Take the time to just double check as you go along.